All right, one quick comment before we do the examples. A function can have no horizontal asymptotes, 1 or even 2, but it can't have more than that. Just 1, none, or 2. All right, so our first example is this limit. And I'm going to actually introduce some tricks and even some forms as we go along. So let's realize what the form is. It's important to pay attention to that because some forms help you understand what the answer is going to be. Other forms are indeterminate, meaning more work. And so here, as x goes to infinity, this whole part is going to infinity, and this part is going to infinity. And so the form is actually infinity minus infinity, and you need to realize that this is another indeterminate form. We'll add that to our list at the bottom. But for now, this means that anything can happen. Maybe these will cancel each other out, and the whole thing is just 0. Maybe the limit will be some number bigger than 0. Maybe the whole thing is going to blow up to infinity. Who knows what's going to happen? So what do? Well, there's a trick here. I need you to not just memorize this problem, but learn the trick. When you see a radical like this, and you've got another term, and you're sort of stuck, it's always a good move to ask yourself, is there a way that I can bring the conjugate into the game somehow? And so let me show you what I mean by that. I'm going to multiply the top and the bottom by the conjugate. So I'm going to take this, and I'm going to multiply by root x squared plus 1 plus x over root x squared plus 1 plus x. And I'm thinking about my function over 1 here to make the multiplication work out. And so I now have the limit as x goes to infinity. And I'm not going to FOIL this out. This is a difference of squares now. So I know that I'm just going to take this part and square it. So the square root's gone. So x squared plus 1. And then I subtract, this part. So squared. So I get a minus x squared. That's great news because I'm going to be able to cancel some stuff. I get an x squared plus 1 plus x downstairs. Cancel this. Let's go over here. So we get the limit as x goes to infinity of 1 over radical x squared plus 1 plus x. And now, if you think about it with me, as x goes to infinity, this part is getting very big, and this part is getting very big. And so the form in this case, I'm going to write it in red, the form in this case is now 1 over infinity. Everything is positive down here. This is all outputting positives. And actually, you know that because x is going to positive infinity. So in that case, this all has to be positive. And so you know from the form that this is just 0. The answer is 0. So that's one example. Let's do another one. So now we're going to take the limit as x goes to infinity of sine of 1 over x. So think with me. As x goes to infinity, 1 over x is going to 0. And so this limit should just be the sine of 0, which is 0. That's true. But how do you actually write that down? Well, let me show you. If you want to, you can make a substitution. So you can say, look, let's call the inside a different variable. You can use whatever you want. I'm going to use t. Let t be 1 over x. And then I'm just going to realize as x goes to infinity, where does t go? Ask yourself, what is t doing? T is going to 0. And then you can rewrite now your limit, the limit as x goes to infinity of the sine of 1 over x is the same thing as the limit as t goes to 0 of the sine of t, which sine is continuous, and so this is just sine of 0, which you know is 0. So that's that one. All right, let's do one more, and then we'll stop the video. What about the limit as x goes to infinity of the sine of 1 over x? So as x gets large, sine just bounces around between -1 and 1. There's no number that it's getting closer and closer to. It's not getting arbitrarily large. So this limit, what do you think? It simply doesn't exist. This limit does not exist. All right, very good. Well, let's do a couple of more examples in the next video, and then we'll call it a section.